Hi, my name is Alex Scarlatos from UMass Amherst, and I'll be talking about our work using simulated students for question difficulty prediction, done in collaboration with Cambium Assessment. Accurately predicting the difficulty of questions is critical to many educational applications. It's needed to ensure the standardized tests, such as the GRE, are fair. It's also used to recommend questions with optimal difficulty to students in learning platforms, such as Khan Academy, ensuring that they're practicing questions at their current level. Finally, it can be used to calibrate the difficulty of AI-generated questions, which are becoming increasingly common in education. However, difficulty prediction is challenging. The most common method involves having real students answer the questions, although this can be expensive and insecure in case students leak the questions. Many machine learning and NLP approaches have been used to predict question difficulty, typically using regression objectives. However, these require a large number of calibrated training questions, which may be expensive to curate. Finally, it is difficult to predict how students will respond to open-ended questions, since there are many more unknowns than structured questions such as multiple choice. Our solution is to use LLM-based simulated students to predict question difficulty, where a diverse set of simulated students attempt questions which will inform how difficult they are. Our primary contribution is a method for training these simulated students called SMART, which stands for Simulated Students Aligned with Item Response Theory. This leverages psychometric models and reinforcement learning to make the LLMs more aligned with real student behavior. Now I'll show how we can use simulated students to predict question difficulty. First, we sample a large number of latent student abilities representing a diverse student population. Next, for each ability, we tell a large language model to respond to the question acting like a student with that ability. Then we use a fine-tuned automated scoring model to provide a score to each generated response. Using this distribution of scores, we fit an item response theory model, which results in latent difficulty for the question. This whole process resembles how real students might be used to predict question difficulty, except where we swap out all humans for LLM agents. I'll go over some background on item response theory, which is a type of psychometric model for representing student scores to questions. In these models, we represent each student with a latent scalar ability, and we represent each question with a latent scalar difficulty. We combine these values to predict the probability that a student will get a particular score to a particular question. We then fit these model parameters using the ground truth student scores. Intuitively, if a student has a higher ability, they're more likely to get a higher score. Similarly, if the question has a higher difficulty, students are less likely to get a higher score. The model shown here represents questions that either get a score of 0 or 1. However, we can use more advanced models to represent questions with ordinal scores, or with continuous scores between 0 and 1. Now let's get back to student simulation. To simulate student responses with an LLM, we prompt the model with the question text and the expected student ability, and then we ask the model to respond to the question according to the given ability. Given a dataset of real student responses, we can fine-tune this LLM using supervised fine-tuning to become more aligned with how real students respond. This brings us to our main contribution, SMART, which improves how well the simulated students are aligned with real students by calibrating with the IRT model. The key observation is that the IRT model tells us how likely a response is based on a student's ability, a question's difficulty, and the score the student gets. Therefore, we can use the probability of a response under the IRT model as a reward function, encouraging simulated responses to be more likely under this IRT model. We use this reward to form preference pairs in the dataset, where we prefer student responses that are more likely for a given ability to responses that are less likely given that ability, and we train using direct preference optimization. The reason this method works well is because it leverages both the calibrated question difficulty and the calibrated student ability to inform the LLM how different students should respond to different questions. We use two open-ended question datasets to validate our methods. The first comes from Smarter Balanced and contains reading comprehension questions at the 6th grade level. It contains only 49 questions, but a large number of students and responses. The scores are ordinal between 0 and 2 and are assigned by real teachers based on rubrics. The second dataset is Code Workout from the second CS EDM Data Challenge. It also contains a small set of 50 questions and a smaller number of students and responses in Smarter Balanced. The scores in this dataset are continuous between 0 and 1, representing the portion of test cases that the student code passed. Critically, the small number of questions poses a challenge for many existing difficulty prediction methods. For both datasets, we fine-tune an LLM to predict the scores of student responses, which we use in the difficulty prediction pipeline. We use two different classes of baselines. The first is direct difficulty prediction methods, which take question text as input and directly output a continuous difficulty value. Similar approaches have historically been state-of-the-art for question difficulty prediction. These include fine-tuning modern BERT on difficulties with mean squared error loss, training a random forest regressor on question embeddings, using KNN to take the average difficulty of similar questions, and using in-context learning with Llama 3.1 70 billion, where examples are chosen randomly or using similarity. The second class of baselines use simulated students, where one uses zero-shot prompting with a pre-trained model, and the other uses an SFT-trained model. We find that SMART significantly outperforms all direct difficulty prediction methods, showing an improvement over previous state-of-the-art approaches. This shows that simulated students are an effective approach for predicting difficulty, especially in settings like ours when there are very few training questions available, only 30 in our case. The direct prediction methods do not get a significant training signal from these questions, while simulated students get their training signal from the large number of real student responses in the dataset. For simulated student methods, when using the 1 billion llama model, SMART outperforms the SFT-trained simulated student, which in turn outperforms the pre-trained simulated student. When using the 3 billion llama model, SMART and the SFT model are more competitive, but both outperform the pre-trained model. We also examine how well the simulated student responses resemble real student responses. We first look at three metrics that compare the distributions of responses in a latent embedding space. SMART and SFT significantly outperform the pre-trained model, with SFT slightly better on Smarter Balanced and SMART slightly better on Code Workout. We also examine the correlation between student ability and the resulting score of responses, which measures how aligned the model is with the input ability. We find that SMART significantly outperforms the other methods on this metric. This helps explain how it's so effective at question difficulty prediction by paying greater attention to the input ability in the prompt. Now let's compare how the responses look for simulated students of different abilities between the SFT and SMART models using a reading comprehension question. In this question, students need to read a report about photosynthesis and are then asked to write an introduction to the report. When simulating low ability students, we see a noticeable difference between the methods. While it's short, the SFT response is partially correct and uses proper grammar. On the other hand, SMART's response better resembles a low ability student by writing an incomplete thought with poor grammar and capitalization. When simulating medium ability students, the SFT response doesn't improve too much and repeats a single idea twice. The SMART response, on the other hand, shows a major improvement from the low ability response, although it still isn't perfect since it doesn't clearly state how plants make their own food. When simulating high ability students, the SFT response shows improvement and answers the question correctly. However, the SMART response makes clearer statements, showing that the model is trying to achieve the maximum score on this question. Overall, SMART contains significantly more diversity across abilities compared to the SFT model, showing that it better represents a student population across these abilities. In conclusion, we find that SMART and simulated students are highly effective for question difficulty prediction, significantly outperforming state-of-the-art approaches on our datasets. We find that SMART succeeds by leveraging improved alignment with the input student ability. In future work, we can expand our student representation. Instead of using a single scalar value, we can use historical responses to questions or descriptive student personas. Additionally, we can apply SMART to dialogue simulations, which are becoming increasingly important in AI-driven education platforms. Thank you very much for listening. If you're interested in learning more, you can find our paper and also our lab's GitHub using these QR codes.